Okay, so we're very happy to have Ying-Hsuan here today to tell us something about contemporary topological insight into 2D SQFTs. Take away, Ying-Hsuan.
Thank you. So thank you for inviting me. So to motivate today's discussion, I want us to first think about the space of QFTs. It's enormous space. There's different dimensions, different symmetries, all sorts of stuff. And one question is, so it has a lot of structures, and it's too difficult to study this whole space, keeping all the structures. So what is some kind of, not really minimal, but what's some structure we can study about this space that's still very interesting, and yet it's simple enough that allows us to say something concrete. So one aspect of the space you might be interested in is so-called deformation classes. So so when we think about quantum field theory, it's not often just one theory in isolation. You can turn on some operators, you can deform it, you do RG flows, etc., etc. So we like to think of the space of QFTs not just with some discrete topology, but there's some kind of continuity in there. And so we can speak of deformation classes. More generally, we can talk about higher homotopic properties. So deformation classes is sort of like asking about the pi zero, just the connected components. But you can ask about, is it simply connected? What's pi one, pi two, etc. And more generally, you can think about this is the common math notation, which is just a map from any space you like X into the space of QFTs and then up to homotopy. And so, so this is the type of structure that we want to think about for the space of QFTs today. And well, so there's this space, and in addition to just these maps and homotopies, there are also some algebraic relations among them. So some very basic operations we like to do for QFTs or just quantum systems. So first, there's stacking, which we also call just product. So just taking the product of theories. We can also take the direct sum of theories, which is basically just putting together super selection sectors. So different universes that just don't talk to each other at all. Well, sometimes we like to isolate out, like we want to say, we want to study a theory that doesn't have multiple super selection sectors. But as I'll soon explain, I mean, if we want to think about deformation classes of QFTs, we're not really allowed to restrict that, to make that restriction, because under RG flows, the number of vacuas, that's not an RG invariant. So there's this sum structure. And then we're not going to talk too much about this, but when you have symmetries, etc., you can do gauging, and then this mathematically introduces a bunch of structural maps. But basically, so we're not going to talk about this gauging and other higher operations today. We'll just think about this product and sum, which basically equips this space with the structure of a ring. So we want to think about the homotopy, basically the homotopy properties of this space and these certain relations. And when we're thinking about deformations, it's very, very useful, in basically any context, it's very useful to think about invariance, deformation invariance, because if there's a certain invariant you can define, and say you associate, you find a theory has a certain invariant, a different theory has a different invariant, then they cannot be in the same connected component, because so for example, some invariants, what might want are like anomalies, like gravitational anomalies, or if you have symmetries, then other types of anomalies. If we have supersymmetry, so SQFTs, then we can also talk about the width index. If we restrict ourselves to supersymmetric deformations, then this is also an invariant. So then the question is, well, there are various questions. For example, for SQFTs, are there invariants beyond Witten indices? And then another question is, so for example, we know that the Witten index is a number. And then in the more general context, you can have something like the elliptic genus. So you can sort of refine this number into some kind of, say, modular form, or you can have some refinement. And those things, as physicists, we often like to think of them just as, some functions or forms with some transformation properties. But given such a function, it's not clear at all that it's actually realizable by a physical system. So are these numbers or functions actually physical observables of consistent physical systems? So this is one central question that we'll say something about. All right, so let me be a little more careful in discussing this notion of deformation classes of QFTs. So so you might know that in condensed matter, they like to talk about deformation classes a lot. And for example, they talk about what's called gap systems with short range interactions. And there, so the rule is that you can deform your Hamiltonian for, say, your lattice system. And deformation classes are separated by phases where the gap closes. So when we define deformation classes, you're not allowed to close the gap in making a transition. And that defines for you sort of what the connected components are, et cetera, et cetera. For QFTs, however, okay, I don't think there's a mathematically rigorous notion of what deformation classes are, but so we want to think of it as basically components that are separated by singular transition. So we're not allowed to make the CFT singular in the sense of having a continuous spectrum when you compactify on a compact spatial manifold. So sometimes we say that a QFT, so sometimes we use the word compact versus non-compact to label that notion. Basically, if your identity in a CFT, if your identity operator is an actual normalizable state or not, or more generally, whether you have a continuum of the spectrum. So that's the type of deformation class. That's sort of a definition of deformation class. In particular, the deformations we do want to include in our discussion are RG flows. And often it's called RG flow up and down. And we don't really have to, RG flowing up, turning on an irrelevant operator is a very subtle business. We don't really have to do that. What I mean by RG flow up and down is just, if you have two QFTs, 1 and 2, and as long as there is some compact, non-singular UV QFT that can flow to both, while preserving whatever you want to preserve, like supersymmetry or some other symmetry, then the loose terminology is that QFT1 and QFT2 are related by RG flows. So first up to the UV QFT and then down back to the other QFT. And yeah, so as I guess said a few minutes ago, when we think about this, because we're studying deformation classes and we want to include RG flows, we are not allowed to say we only have, we're not allowed to demand only a unique ground state, because that's not an RG invariant. When you go to the deep IR, very often, as we'll see in a concrete example later, that multiple universes can appear, super selection sectors, basically. So as I said before, that requires us to have this sum structure, direct sum structure, not just the usual product we like to think about. And one thing that I think can be a little confusing for people not used to thinking about this sort of homotopy structure of the space of QFT is, well, when you have supersymmetry, okay, so usually let's say you have a generic QFT with no supersymmetry, then when we say we flow to the deep IR, right, we're basically saying, okay, this system has a ground state and we're just flowing very arbitrarily close to that ground state. So the IR scale is essentially set by the ground state. But when you have supersymmetry, there's another absolute notion of an IR scale. Because, so let's say you put your quantum field theory on some compact spatial manifold, it becomes some kind of quantum mechanics, and where the spatial manifold preserves supersymmetry. So it's for example, if it's 2D, then you want to put a Raman periodic boundary condition for your fermions. Then we know that, well, the Hamiltonian or the energy, the supersymmetry algebra says that H, or the energy, is equal to Q squared. And so this basically sets an absolute scale for what we mean by zero energy. We're not really allowed to, just arbitrarily add things. So there's a difference. I think this often confuses people when they first think about this. So there's a difference between 1 and 0 as the Witten index. So 1, if your Witten index is 1, it says that there is a unique, well, you can have a unique, I shouldn't say Witten. So let's not think about Witten index, just there's a notion of 1, which says that there's one ground state, but there's also a notion of 0, which means that your ground state is above this absolute 0 that's given by a supersymmetry, this Q squared 0. So you can basically flow below the actual ground state you have, and then you have actually nothing. That's actually 0. And what this means is that essentially your theory is in a phase where SUSY is spontaneously broken. Because remember from our basic supersymmetric quantum field theory that the supersymmetry is preserved if and only if the ground state is 0, has energy 0. Okay, so now, depending on your view of QFT, whether you like Lagrangians or axions, et cetera, the way you think about deformation classes can be abstract or can be concrete, but it would be very nice to have some kind of geometric model or geometric mental picture when we think about these deformation classes. And so a very useful set of QFTs think about are sigma models. So as we all know, a sigma model is some quantum field theory where the fields are valued in some target manifold M. So the scalars are valued in M, and then you might have fermions valued in the tangent bundle of M, etc. And of course, it was originally invented in the 60s to describe pions and chiral symmetry breaking. Now, so here I'm talking about nonlinear sigma models. And this is actually a very tricky business if you want to think about if you want your system to also have supersymmetry. So when you have supersymmetry, you necessarily need fermions. And so we know that when your system has fermions, there can be all sorts of anomalies that one has to worry about. So just saying that I have a supersymmetric sigma model on some space M is often not enough. It's not precise of a statement to make, because sometimes the consistent quantum theory doesn't even exist. There are some bad anomalies that renders the path integral inconsistent. So basically the upshot is that, well, if you want a sigma model and you also want some kind of supersymmetry, then the target manifold M actually often has to have more structure. And I'm sure everyone here is pretty familiar with this. Like if you want extended supersymmetry, you might want it to be a Kähler manifold or hyperkähler, et cetera, et cetera. And one example that we're all familiar with is the heterotic roll sheet. So, so to formulate a world sheet CFT or theory for the heterotic strings, so there's some non-compact direction which we can just take to be flat space, this R10 minus D, and then there's some internal manifold. Well, yeah, so internal part MD, and this internal CFT. So first of all, it's heterotic. So the supersymmetry is 0, 1. I'm using the convention that it's supersymmetric on the right. So I'm just going to call it the right. And so it's a sigma model with this target M. But there's also, so, heterotic string also has all these left-moving either fermions or bosons. So basically it's some kind of holomorphic vector bundle. More generally, you have some base M and you're allowed to just equip it with more structure. So that's basically, I'm using just this V to denote the fact that you can add a bunch of more data into your definition of your theory. This world sheet theory, well, it's left-right asymmetric. The central charges are different. There's gravitational anomaly. And then there's also a bunch of anomaly cancellation conditions, which indeed requires that MD has to have some extra structure. It's known as a string structure, but the precise definition of that is not too important. I can just give an example where, suppose we're not talking about heterotic. So suppose we take the V to be trivial. So the E8 is just standalone. It's like not talking to the internal alpha at all. Then you cannot take MD to be K3, for example. It turns out that that's just inconsistent. And of course, in our usual language, we know that, yes, that's because we have to embed the holonomy into the gauge bundle, and that's how you make it consistent. Now, so I gave heterotic string as an example where sort of this extra holomorphic vector bundle is important. But now let's sort of ignore that for now, and let's talk about the geometric deformations of the sigma model. So what I mean here is, well, the sigma model is a quantum field theory, and you can deform it in many different ways. Some of those deformations can be considered geometric in the sense that you're still within the class of sigma models. You're just changing the M or changing the whatever structure you put on M. And these geometric deformations are characterized by bordisms, which I depict in this cartoon here. So a bordism is, so you have some manifold M and a different manifold of N that they're the same dimension, capital D. So a bordism is some manifold in one higher dimension whose boundary is precisely this M with the orientation reversal of N. And the claim, well, so basically the picture for sigma models is that if you have such a bordism, then the sigma model on M can be continuously deformed within the class of quantum field theories and the sigma models to this N. And if you think of this process as, if you choose some kind of foliation for this bordism, so a generic bordism will have some kind of, so this point looks singular if you choose some foliation that passes through here. And the way to think about that is just that it's the equivalent of what we said before, that when you do RG, sometimes you can generate degenerate ground states. So you see, once you pass this point, you have your spatial slice your slice has two disconnected components. And when your target space has two disconnected components, that just basically means you have two universes. There are two parts of the QFT that don't talk to each other. And so this is sort of,
sorry, I have a quick dumb question before you go on. This is something basic. I should know it, but I'm embarrassed to say I can't recall. If suppose you have two spaces that are birational to one another, can you necessarily find a bordism connecting them? But the reason I ask is that I can build gauge linear sigma models, which will give a smooth path in the space of quantum field theories that will join often but not exclusively birational spaces. So that sort of strikes me as being another example. In what you described, if I'm following you correctly, you're describing geometric bordisms in the sense of you have two spaces, you find that's still a geometry, but but I can play games with, having essentially two sigma models, two weakly coupled sigma models on geometries that are related by some sort of path in, in the space of quantum field theories. And I should know this, but just staring at that picture, I don't know whether it can be encompassed in, but it's a question I could ask you later. If you happen to know off the top of your head, I was curious. If not,
I see. Oh, I don't know, but yeah, I don't know. But if the claim is that if you give it any birational equivalence, you can build a cobordism, then
I guess that's the question. I'm not.
Oh, that's the question. I see.
Yeah. It's not essential.
That's not clear to me, because I think it should be false. The converse should be false, right? Like if you have a cobordism, it's not true that there's always a birational equivalence. So yeah, so the connection is not clear to me.
Okay, fair enough.
Yeah, I never thought about that. Right, so thanks for the question. So moving on. All right, so this is sort of the picture you should have for geometric deformations. But as a quantum field theory, there can also be non-geometric, more general deformations. And sometimes colloquially, we call it quantum cobordism. Quantum cobordism is not just like one cobordism. There's a lot of extra data you specify. So we're going to focus on a particular type of quantum cobordism later. But so let me give an example of some deformation that isn't really geometric, in the sense that I'm not going to formulate it in terms of some sigma model and describe this deformation geometrically. So let's think about some, one of the simplest families of supersymmetric quantum field, actually conformal field theories, which are the n=1 minimum models. And also to distinguish 1,1 from 0,1, I explicitly wrote out 1,1, but okay, that's not too important. So let me remind you that these models are labeled by some integer little m here. This little m can take values in this convention, 2, 3, 4, etc. This is the formula for the central charge, and you can see if you plug in m=2, it's 0, so it's just the trivial theory. Putting in 3, you get 7/10. That's the tricritical Ising model, and you get a family, so on and so forth, with the central charge bounded by 3/2. So this model, if you go and compute it's a Witten index, you find that for m odd, it's 0. For m even, it's 1, essentially. There's a sort of sign convention, but so just take it to be 1. So it just depends on the even oddness of this parameter little m. Now, the statement in essentially very old literature is that, well, there exist supersymmetric RG flows connecting any successive, any from T sub m to T sub n-1. So the neighboring minimum models have some supersymmetric RG flow connecting them for all m. So this is, there's this statement, but you immediately realize that this statement it has to be somewhat refined a little bit. Otherwise, there's a clear contradiction, because the Witten index is a supersymmetric invariant. So, if this sentence is true, then there's a jump in the Witten index. Now, so how do we understand this? So there's a very nice way to understand this, which is to think about, so these minimum models have very nice realizations in terms of supersymmetric Landau-Ginzburg models, just like the usual non-supersymmetric minimum models can also have some LG description. And so in the supersymmetric world, these models are specified by a superpotential here, this W, which is some polynomial in the superfield. And let's take its degree. So its degree, having degree m-2 gives you the nth minimum model.
So I've got a dumb question. Are these minimal
Yeah.
models, are they really n equals 1 or n equals 2? When I think about a superpotential in 2 dimensions, I usually think about 2 comma 2 SUSY. And certainly there were superconformal, n equals 2 superconformal minimal models. I can, in fact, there's the A series, which it sounds like you're leading towards. And then I could imagine some information, but if you're talking about superpotentials, are they really n equals 1 or are they n equals 2?
Oh, sorry, am I using the wrong terminology? So I'm definitely talking about n equals 1. Maybe I
Okay.
shouldn't, let's see, should I call? Yeah, I think it's okay to call this super potential. Yeah, no, I am talking about n equals 1. So
Okay.
yeah, if the standard convention is, 2 comma 2 is the Calabi-Yau type of sigma model, then I'm talking about fewer supercharges, so 1 comma 1.
Yes.
Yeah.
Okay.
Yeah. All right. So right. So from this superpotential, it follows that the scalar potential is you take the derivative of it and then you take the absolute value squared. So if you take the derivative, then of course the degree is decreased by 1. So it's degree n minus 3 now. And how do we, yeah, so let's draw a picture. So here, let's think of this as, so this is like the superfield space. If you have W of phi, then, so the overall sign of W doesn't matter. Let's fix the sign convention such that when phi is near plus infinity, it has positive slope. And then depending on n, at negative infinity, it either has this positive slope here, or it has this negative slope like this. And then the general, I mean, we're talking about, so we're sort of allowed to choose this superpotential if we're allowed to sort of deform the theory in some continuous way. And basically, the Witten index is computed by looking at the intersections with 0. So the Witten index only counts ground states, and therefore we only care about points where this W prime is 0. So for example, you could connect things like this, and this you get 3 points. And the rule is that depending on the slope, if it approaches 0 in one direction versus another direction, you count these states with different parities. So you can easily convince yourself that, well, the sum of these things is a topological invariant. It doesn't matter how you wiggle this green curve. If you start here and you want to go down here, then the net result is you're going to have one net crossing. So the Witten index will be 1 instead of that would be 1. And whereas if you're in the M-odd case, then it's easy to see that, well, you cross an even number of times with opposite parities, where the parities pair up, so you get 0. So that's sort of how you see this. And
so just so I'm following correctly, the theory TM then is described by a superpotential that's a polynomial degree. It's either M or M plus 1. Is that right?
Yeah, M plus 2.
M plus 2. Okay.
Yeah. So yeah. Yeah. So right. So let's take the simplest example of this purported RG flow. So let's take the first non-trivial theory, which is the tricritical easy model. This is M equals 3. And it has Witten index 0. So the claim is that it can flow to the so M equals 2 theory, which is the trivial theory, which has Witten index 1. So it doesn't have Witten index 0. And the resolution of that is, well, it doesn't actually flow to just that theory. It actually flows to a direct sum of that theory together with a theory that's almost essentially trivial, but it has the opposite sign for the Witten index. And I'm sure you're familiar with this notation. It's not too important. That's just what I wanted to explain. So the total Witten index will remain 0. And so sort of this old statement, this statement here, is essentially thinking about some higher or more general M and ignoring so there's always some accompanying trivial theory that they essentially just ignore. And but it's clear that it does give a contribution to the Witten index, which is, say 1, and it makes the Witten index still conserve under the RG flow.
So can we see that just in terms of messing around with these polynomials? It's a statement that if you take a polynomial of degree m plus 2 and then, I don't know, multiply it by a factor or factorize it so as to reduce, either increase or decrease the degree, is the point then that let's suppose the superpotential factorizes so that you're decreasing the degree of at least piece. What are you doing to the superpotential? Maybe that's the question I should ask.
Good. So yeah, I'm not sure how to think about the algebraically in terms of like factorizing, but from the picture, it should be very, very clear. So this blue curve here is the superpotential for the tricritical Ising model. It's fine-tuned so that it's sorry, I shouldn't say this is W. This is W prime.
Okay.
Yeah. So it's fine-tuned that it has this double zero here. And the general deformation, as you said, is, well, I can just wiggle this potential whatever I want. The deformation that characterizes this RG flow is to basically lower this curve and just keep lowering it so that the points where it crosses zero become infinitely far away in field space. Right. So where they cross zero are these red dots, which in the deep IR are represented by the trivial theory and then sort of the reversal, the minus the trivial theory. And then if you lower this potential like infinite distance, just lower it, keep lowering it, then these 2 points become so far away that they're essentially different universes. They become super selection sectors.
Okay.
Yeah, and and it's easy to convince yourself that whatever this picture generalizes for arbitrary m. You're just wiggling. So to flow from Tm to Tm minus 1, you're just deforming your superpotential in a way such that you're keeping n minus 1, most of the zeros on one side, and then deforming it so that there's 1 0 just like moves infinitely far away in field space, and so it decomposes into this direct sum.
I see. So the extra theory you're adding is something off at infinity. Is that the way I should think about? This is ultimately some exercise in compactness issues. Okay.
Yes. So the horizontal axis in this picture is like the field space, right? So you should think of that as this. It's like a coordinate for the target space. And as we said before, if the target manifold has 2 disconnected components, then that corresponds to universes. And that's essentially what we're saying here, that if the 2 zeros are infinitely far away from field space, it's essentially kind of like we're saying they're in disconnected components of the target manifold, and that's how I think we should think about that. And then here, let me just quickly also make a point about the statement I said before about supersymmetry, spontaneous supersymmetry breaking. So that was a very general statement, but here you can very explicitly see that, well, if you deform this potential not going downwards where it still has zeros, but you move it up, then clearly supersymmetry is spontaneously broken. And in the IR, you flow to the non-supersymmetric Ising model. Right. Okay, so we've gone through a sort of a long discussion about basically a lot of it was old stuff, nonlinear sigma models, n equals middle models, cobordism. So what is really the new sort of contemporary topological insight that is in the title of my talk? So this brings me to this subject of topological modular forms. But let's okay. So I hope I guess in the past half hour, I've convinced you that the space of SQFT in D dimensions, not the target dimension, which is capital D, but the I guess world volume. I think space-time is a very confusing word for string theory, so let me call it world volume dimension, little. So this space of SQFTD modulo continuous deformations define some space, this script S. The highly non-trivial claim is that, well, this space it's a very complicated space. But if we forget about a lot of its structure and only care about its homotopy, then it's actually homotopy equivalent to a different topological space that's defined in a completely different, like purely mathematical manner. And that depends on what little d is. So for d equals 1, which is supersymmetric quantum mechanics, this E is equivalent to something called the KO spectrum. So that's not the main focus here. So we're focusing on d equals 2. And the claim is that the space S is homotopy equivalent to, think about it as a topological space. And so it's commonly known as topological modular forms, but sort of just being more careful, I don't necessarily want to think about this TMF as just an abbreviation. This is basically I'm talking about topological space, or more precisely, it's some spectrum.
Good.
So this is, yeah. So this claim is so this is due to Stoltz and Teschner. The quantum mechanical case is proven. So this is a rigorous statement that if you look at deformation classes, preserving supersymmetry, so there's a certain, I don't want to get into this, but there's some Clifford algebra you define on your supersymmetric quantum mechanics, and depending on the dimensionality of Clifford algebra, the deformation space is different. So there's a relation to KO theory that's actually rigorously proven. And but then, we all know that the mathematically rigorous definition of quantum field theory is a very difficult problem. So it's not too surprising that if I tell you that the d equals 2 case is a conjecture, but there's no known counterexample. So that's sort of what the interesting thing is. There's this very mysterious conjecture. Okay, so I'm not a mathematician, but let me try to give you a flavor of how people constructed this TMF. So well, when we think about quantum field theory, it has a lot of data, but the particular aspect of it, one of our favorite things to talk about for a quantum field theory is the partition function. Partition function on all sorts of, say, closed manifolds, right? So we believe that if we're given a consistent QFT, and you give me any closed manifold with, some appropriate amount of structure, then it spits out for me the partition function, which is basically some complex number that depends on sort of the parameters. So you think of it as a number or some function from the parameters to the complex numbers. So that's the partition function. In the case of little d equals 2, if I think about a torus with periodic boundary conditions for fermions, so Raman boundary conditions in both sides, okay, so geometrically, it's of course a torus, but algebraically, it's more precise to say it's an elliptic curve, characterized by some kind of Weierstrass form, and the algebraic abstraction, that abstraction is useful because then you don't necessarily have to think about, a variety in C. You can actually define it over any ring, and the technical term for that is it's a Hoff algebroid. Basically, you have a Weierstrass form, all the coefficients, you think of it as in some ring, and you quotient out by some transformations that define for you equivalent curves. So that's just a side comment. But basically, if you take this, then it's very natural to think about, think about a family of elliptic curves, not just a single elliptic curve, but a family of elliptic curves. So if you're given an SQFT in 2 dimensions, and you compute this, you put supersymmetric boundary conditions in both space and time, then we like to think of this partition function as some section of a certain, bundle or sheaf over the moduli space of elliptic curve, moduli stack or moduli space of elliptic curves. And if you just think about, right, so this is one way to think about what a modular form is. It's some section of some bundle over this. But there's a much more sophisticated way to, okay, so I don't really know the mathematical definition, but Hopkins et al. Defined a certain sheaf over this moduli stack. And when they take the global sections of it, it defines for you this TMF. And that description might sound a little abstract, but TMF is very, very closely related to MF. It's a refined version of MF. And they're related in the sense that there is a map from TMF to MF, as we'll soon see. But let me just first tell you, so you might notice that I have a little subscript here, which is nu. And so what is nu? Nu is the gravitational anomaly, which I normalize such that it's an integer. If you like to think about CFTs, then this is defined as twice the chiral central charge, C right minus C left, where right is, in my convention, the supersymmetric side. So this chiral central charge is a half integer or integer. So if I multiply by 2, then it's an integer value. All right, so as I just claimed, there is a mathematical map from TMF to MF. And the modular form is over the integer ring, the Z ring. So some properties of this map is, well, first of all, it's not injective. Okay, so there are certain, so you should think of this TMF as giving you some supersymmetry invariant. So any supersymmetric deformation does not change the class. But the fact that it's not injective means that there exist SUSY invariants that go beyond the usual Witten index for elliptic genus. Of course, in some cases, when you have extended SUSY, like you have like a T4 split model, we're familiar with this fact, right? Because the elliptic genus vanishes and you have to do some modification of it. Here, it's of a similar flavor, like you have to be more clever to find what this supersymmetry invariant is. But it's also a lot more subtle than just the modified index, because the modified index is still something that's sort of C valued. It's like something a function that's very concrete that you can see. But a lot of these things that lie in the kernel of this map, they're torsion valued, which means that if you take, you cannot associate them to usual numbers, because if you take the direct sum of, say, 2 copies, sometimes it becomes 0. So it's torsion value. So this is an interesting story, but I'm not going to say more about this non-injectivity. Another very surprising fact is the non-surjectivity. So not all modular forms with integer coefficients are actually realizable by SQFT, if we believe in the conjecture. So to give you a flavor of what this non-surjectivity entails, let me first tell you that, well, the whole ring of modular forms is, you can think of it as having these generators, the E4 Eisenstein series, the E6 Eisenstein series, the modular discriminant, and its inverse. And here I'm using the normalization where the leading coefficient of the Q expansion is 1. There's no like funny 2 pi factor in certain conventions. So there's this ring, but it's not freely generated because you have to quotient out by this one relation, which just expresses the relation between the modular discriminant and E4, E6. If we were working rationally, then we don't even need this delta, because you can always express these deltas in terms of the E4, E6. But because we're working over integers, we do have to have these deltas. Just having the E4, E6 is not enough, because you wouldn't be able to form delta itself, for instance, because of this 12 cube factor here. So the non-surjectivity is the following claim. The image of this TMF to MF map has an integral linear basis which is given by the following. So I'm not going to tell you too much. Okay, the most remarkable fact about this is when is for the term where there's only delta. So when I and j are 0, there's no factor of either the E4 or E6 Einstein series. There's just a modular discriminant. Then the coefficient has to be divisible by some non-trivial number. And that non-trivial number is given here. Another way to express this, I think actually is a little more convenient, is to say that 24 has to divide this A00K times K. I think this is probably easier to remember than this GCD formula. All right, and okay, let me spend 1 minute to make some comments before we go on to the example I want to discuss. So I was talking about TMF as a topological space, but more precisely, it's a spectrum in the sense of stable homotopy theory. It's a spectrum for a generalized cohomology theory, which is this first thing here. So cohomology means taking some space X and map it into the spectrum. But once you have the spectrum, you can also talk about homology, which is the reverse. You take this spectrum and then you map it into some space X. And there's some, so if you're familiar with KO, you might know that there's some bulk periodicity. There's something very similar here, but the periodicity is much, much bigger. So it's 576. So, and it's given by multiplication by this invertible element, which is delta to the 24. So notice that because of this formula, delta itself is not invertible. But if you raise it to the 24th power, then it is invertible. And so the periodicity is given by this. And then just since we've been talking about sigma models, given a, sorry, I shouldn't say bordism. I should say, sorry, this is not, I don't mean bordism. Well, I mean bordism class. So if you're given some target space, the claim is that the sigma model on that target space gives you some class in TMF, which if you map to modular forms is precisely the Witten index or the elliptic genus of that sigma model. So now I'm going to talk about a simple application of this conjecture or this set of ideas, which concerns holomorphic CFTs. And so general 2D CFTs are kinematically factorized, but they're not really, they're not truly factorized because as we all know that for locality reasons, you have to have some kind of non-trivial modular pairing, et cetera, et cetera. But there is a very special class of 2D CFTs that are factorized, and they're called either chiral or holomorphic CFTs. So there's some variation in the definition, but I'm using one definition where you demand that the central charge has to be a multiple of 24. By holomorphy, the partition function on a torus has to take the following form. So there's this J function that I think you're most likely familiar with, which is defined this way. And it's given by J to the nth power plus dot, dot, dot. So J to some coefficient times J to the n minus 1, all the way to the constant coefficient. So it depends on finitely many coefficients. And now let's try to apply this TMF conjecture. So what does, so I've been talking about SQFTs, and supersymmetry is important in that conjecture. But the holomorphic CFT, so first of all, it is a special case of SCFT, and which is a further special case of SQFT. So you should think of holomorphic, even though we don't usually think about supersymmetry when we talk about holomorphic CFTs, it really is a boundary case of a supersymmetric quantum field theory. So if we go back to sort of this picture of SQFTs, then there's some RG flows you can do and will flow to some SCFT. The generic SCFT is some blue, and I call her in blue. And then for some special cases, you just get a holomorphic theory, which is this red piece. So it's some special corner of it's some special corner of this whole space of SQFTs. So if you look at this picture and you believe in the Stokes-Deschner conjecture, then well, we take this partition function, this form parameterized in this way, and we demand that it lies in the image of this map. What we find is that, well, 12 has to divide, so n is this parameter for the central charge, and times this constant. So it only constrains the constant piece in the partition function. So that's the claim. And it seems like a surprising claim. Well, at least when I first realized this, it seemed pretty surprising to me. So I immediately went to look at examples. For the simplest example, C equals 24. This is famously classified by Schelikens. And you can just look at his list and you see that this is true, that the number of spin one currents is always a multiple of 12 somehow. Going higher, there's no classification when you go above C equals 24, but there are some constructions given by lattice VOAs under some orbifolds. And I look at those 100 odd examples, and they all satisfy this condition as well. And then you can go further. So then we also try to generate our own examples, which there's a large class one can generate by taking the products of moonshine theory, so like either monstrous moonshine or Duncan's super moonshine. And so the reason why I want to use moonshine is that there's a very large global symmetry group, discrete symmetry group, that I can further orbifold by to produce a large family of theories. And if you do that, basically you generate infinitely many examples that all satisfy this property. So it's, well, I consider this very non-trivial evidence for the conjecture, and at least personally, I have no doubt of the conjecture, at least in this form. And then there's an application of this result to, well, an interpretation of this result in the context of quantum gravity, which goes back to this very old conjecture. Well, this conjecture from like 15 years ago. So there's a conjecture by Hone that there exist extremal CFTs, which are holomorphic CFTs, where you try to make the gap as large as possible without violating unitarity. And then Witten conjectured that, well, this is such a nice family. If it has any significance in holography, it's probably due to some very nice theory. But if you go and look at those partition functions, they don't satisfy this condition. So as a believer in the TMF, the Stokes-Deschner conjecture, I would consider basically this wishful thinking ruled out. So that's one application to quantum gravity. And then, so I'm almost out of time, but I do want to, because sort of this is why I asked you some questions before. This is still very much under development, but there's another context. So, okay, so let's recap a little bit. So if you have a sigma model, or you have some quantum field theory that has some amount of supersymmetry, and especially if it has gravitational anomaly, then there are some very non-trivial constraints on what the elliptic genus is, or some refined elliptic genus is. And so, of course, we've covered periodic Rossi. That's one example where this occurs. There's another context where potentially there's a very rich family of quantum field theories that can be constructed this way, and also has to do with algebraic geometry. So that's by taking some Calabi-Yau threefold, looking at some divisor, and then wrapping, let's say, a single N5 brane on that divisor. You wrap it on a 4 cycle, and so you have 2 remaining directions left, and you do some RG flow. That gives you what's often called the MSW CFT, N5 brane CFT. And for the simplicity of discussion, let's say we are considering some one parameter Calabi-Yau. So the key geometric data that goes into the characterization of the CFT is, first, there's the self-intersection, kappa. I'm using a convention here where kappa itself is an integer. So sometimes it's written as like 4, depending on notation, but I don't have that 6 in my definition. And then there's also this integral of the Kähler class over this P. So there's two pieces of data that basically, given your construction, algebraic geometric construction of your Calabi-Yau, one parameter Calabi-Yau threefold, you can compute, these are computable data, or one of the first things you want to compute. So in addition to this, there's some Lagrangian analysis by these gentlemen. So they take the Lagrangian, some M5 brane, and they analyze the field content of M5 branes and think about what happens when they compactify. They, in my more modern understanding, this is the picture that they arrive at. So this is a theory where I want you to think about as a 3D TQFT having two boundaries. One boundary is kind of, I wouldn't say boring, but like it's free. So it has a bunch of free bosons, free fermions. It's what these gentlemen call the universal part. And this is not a good theory on itself. It's a relative theory, namely it's the boundary of a certain non-trivial MTC, some ZK MTC in this 3D TQFT. What's interesting is the other side. The other side is, so this theory has 0,4 supersymmetry. And this partly comes from the Lagrangian analysis, which suggests that it's a hyper-Kähler sigma model, but equipped with additional holomorphic vector bundles. Very similar to, let's say, heterotic string on K3. So you have not just the K3, but you also have like an E8 or SU2 bundle, non-trivially fibered over the K3. And so this is kind of an old story, but basically this is sort of the pieces of wisdom that people have about the CFT. So a very simple example here is this what's known as X66. It's one of the one parameter Calabi-Yaus that have self-intersection number 1. And if you look at, so there's a formula for the dimensionality of the hyper-Kähler manifold in terms of these two numbers. And it turns out that it has to be K3. So it's a K3 base with some holomorphic vector bundle. And the fact that kappa is 1 means that actually the MTC in the middle is trivial. So it's just a product. It's just stacking some free bosons fermions with a hyper-Kähler sigma model, right? So we don't, the whole complication of being a relative theory on this side goes away if you only look at kappa equals 1. And then you look at the elliptic genus. It's exactly the same as heterotic string on K3. I guess E8, E8. Well, so this is part of the confusion I had, which is I don't know. I know how to compute the standard embedding elliptic genus, but I don't really. I think it's probably the same for all embeddings, but I'm not so sure. So
if you deform, so that I can answer off the top of my head. If you have a non-standard embedding which can be deformed to the standard embedding, if you have a gauge bundle which is the deformation of the tangent bundle, then the elliptic genus will match. But if it's different, the elliptic genus could be completely different. Or well, let me be careful. The elliptic genus doesn't really have that many parameters.
Yeah.
Okay, so that's your point. If you have a different bundle, then because say a different bundle of the same rank, so the central charges match. Yeah, okay, actually, you have a good point. Yeah, I never mind. I'm not sure.
Yep.
Certainly in the easy case, I'm just telling you stuff you already know. In the easy case, if the gauge bundle can be deformed to the tangent bundle, then the elliptic genus matches. But if the gauge bundle, however, if the gauge bundle cannot be deformed to the tangent bundle but has the same rank, it might still be the same. I'd have to check.
So yeah, so I thought they're the same because of this paper by Shapir and Tachikawa, where if for higher dimensional hyper-Kähler, it's more complicated, but for K3, it seems that there's a universal formula that depends only on the rank. And
yeah, that sounds.
So
the thing that's confusing, the thing that always confuses me about elliptic genera is, sorry, I'm just wasting everyone's time, but naively, it looks like some infinite series. It looks like you have infinitely many constraints on if you want to get things to match. But in fact, modularity means that you really only have some small finite number of parameters. So they're just things like ranks, central charges, and if those match, the elliptic genera match. Yeah, Fair enough. Fair enough.
Yeah,
All right.
and so what's more, okay, if we believe in the Stokes-Dessner conjecture, then the statement is that any two 0, 1 theories with the same elliptic genus can be deformed to each other by 0, 1 preserving deformations. So
Yeah.
on the string, if you want to think about how to draw a string on the string world sheet, well, I guess one common point of view, if you have to deform away from CFT to SQFT, then people often say this is like some off-shell process in string theory, even though I'm not sure how precise it's really been made in the literature.
That's all good.
Yeah.
That's all good.
Yeah, but so if we take that statement, then it seems like, at least for K3, the topologically different non-standard embeddings should be, there should be a way to deform them. You might have to break 0, 4 into 0, 1. And I thought I don't know, maybe it's too difficult a question to actually realize this very concretely, but it seems like an interesting question.
That's true.
And then, yeah, and then more generally, I mean, here this is just one example. And there are tons of Calabi L3 folds, tons of MSW CFTs one could construct. Presumably a lot of them have kappa equals 1. And let's just consider those so we don't have to think about relative theories. If we believe that they are hyperkähler sigma models, one thing that really interests me is, like, can we really identify the topological properties of that hyperkähler base? In other words, I'm not sure. Maybe you know, like, if I have like, say, two different topologically different hyperkähler manifolds, let's say hyperkähler manifolds with different Hodge diamonds, and I'm allowed to put some holomorphic vector bundles on them, so they become, let's say, some 0, 4 SQFTs, and then I allow, can they be? If I don't have the vector bundle, we shouldn't be able to deform them into each other. But okay, even that I don't know. But if we
if you have the vector bundle, it gets more complicated, at least at the level of the superconformal field theory, indeed at the level of the superconformal field theory. Sometimes you can do some very non-obvious deformations. Now, the deformations in question will go through the space of quantum field theories. And this isn't just about 0, 4, this is about 0, 2 as well. There are some nice examples by, well, several groups now. I think the original examples that come to mind were by Dissler and Kotru, that constructed a family of not just random deformations, but actually deformations through supersymmetric vacua, essentially deformations through the space of not just supersymmetric quantum field theories, but deformations through the space of supersymmetric conformal field theories that could link bundles of, different looking bundles over spaces. And more generally, this is a game with GLSMs, but there's a particularly funny version that Dissler and Kotru worked out in 0, 2 theories. I'll see if I can send you a reference later to look at. But there was a broader story that just GLSMs provide you a mechanism to do deformations in the space of superconformal field theories, deformations which don't necessarily, or at least don't obviously to me, come from geometric deformations. You can do deformations in the space of quantum field theories or in the space of conformal field theories that don't obviously correspond to deformations of geometries.
Right.
Anyway, that's neither here nor there. Actually, I think we're going to be kicked out of here in a few more minutes.
Oh yeah. So
please continue.
Yeah, let me try to close. So sorry if to other people in the audience this seems like a digression, but this basically I just want to say that there seems to be a lot of examples actually in string theory or M theory where TMF or just basically SQFTs with chiral gravitational anomalies can, there's some very interesting zoo of theories that we can explore. And this is also tied to, so I mentioned that this has 0, 4 supersymmetry. So we can ask, well, let's go to this point. So if I demand that the deformation has to preserve, say, some higher SUSY, not just 0, 1, let's say 0, 2, 0, 4, or 2, 2, is there some corresponding interesting theory of TMF that also tells us something very non-trivial? We can also ask about the equivariantization of TMF, so we can add in discrete symmetries. It could be either group-like, or it could be some fusion category, or more generally. So we can think about relative theories, right? Like here, I can just ignore this free part altogether, and we can ask, is there some version of TMF that tells us about the space of all theories that live at the boundary of some zk topological order? And this is very much under, people haven't really, I've been discussing with some mathematicians about this, but like it's very much unknown. But this would be very, very nice, because basically all rational theories are in a sense holomorphic. It's just holomorphic, but they're relative to some non-trivial 3D bulk. So if there's a way to discuss TMF as relative theories, as boundaries of non-trivial 3D TQFTs or MTCs, it's essentially a new handle to classify RCFTs. So not just holomorphic CFTs, but general RCFTs. And I think this is something that's very worth developing further and working more about. And then finally, there's this thing, I've been thinking about for a long time. I couldn't make any progress, which is there a physical, a complete, is there a physical explanation of this TMF constraint, purely using just the usual axioms we have for 2D quantum field theories, like locality, causality, this type of thing. And so far I have no clue. So let me close there and see if there are more questions.
This is a fine talk, and I've got questions. I can imagine a bunch of questions, but there's also a crowd outside the room.
Okay.
Maybe in that spirit, I should just I'll try to remember to email you some references on GLSM. So you probably already know the story, but just wrap up that end of things. And let me not. I've already asked a bunch of questions. Xingyang, do you have any?
Yeah, I also have like a bunch of questions and other things, but I think let's
let the next crowd.
Yeah, right. I think I will send you an email about someone.
Okay. Yeah. I'm happy to continue the conversation over email or.
Yes, right. Yeah. Especially for this relative chiral CFTs as the 3D bulk boundary and how to see this from the TMF. I'd be interested in that part like for a long time. Yeah. Yeah, let's talk about this later.
Okay.
I think.
All right, let's
Okay. Thank you so much.
Okay. Thank you.
Right, thanks again.
Bye-bye.
Take care. Bye.